Problem analysis in data structure and algorithms. Problem analysis is a crucial step in developing effective solutions using data structures and algorithms. It involves thoroughly understanding the problem, designing appropriate algorithms, and validating the implementation through testing and debugging. Importance of problem analysis. Effective solutions. Thorough problem analysis leads to the development of optimized algorithms and data structures that solve the problem effectively, reducing complexity. Understanding the problems, constraints, and requirements helps identifying the appropriate approach to minimize time and space complexity. Avoiding pitfalls. Problem analysis helps anticipate and address potential issues, ensuring a robust and reliable implementation. Steps in problem analysis. Understanding the problem, clarify, define the problem, its inputs and outputs, and any constraints or requirements. Designing the algorithm, develop a step-by-step plan to solve the problem, considering different approaches and their trade-offs. Implementing the solution, translate the algorithm into code, ensure the implementation matches the designed solution. Understanding the problem, identify inputs and outputs, clearly define the problem's input, expected outputs, and any additional requirements or constraints. Analyze edge cases, consider potential edge cases and boundary conditions that the solution must handle correctly. Understand the context, gather information about the problem's domain, and any relevant background knowledge. Break down the problem, divide the problem into smaller, more manageable sub-problems to simplify the analysis. Design the algorithm. Identify patterns, looking for recurring patterns or similar sub-problems that can be solved using techniques. Evaluate approaches. Consider different algorithmic approaches and their trade-offs in terms of cost, time, and space complexity. Choose an optimal solution. Select the most efficient algorithm that meets the problem's requirements and constraints. Flowchart and creation. Visualize the algorithm. Create a flowchart or pseudocode to represent the step-by-step execution of the algorithm. Identify data structures. Determine the appropriate data structures to store and manipulate the problem's inputs and outputs. Refine solution. Iteratively improve the algorithm and data structures to optimize performance and correctness. Programming. Translate to code. Implement the algorithm in programming language. Following best practices, coding standards. Optimize performance. Analyze the code for potential performance bottlenecks and make necessary optimizations. Write clean code. Ensure the code is well structured, readable, and maintainable for future modifications. Compile and execute. Compile. Ensure the code compiles without errors and warnings. Execute. Run the program with various test cases to verify the correctness of the implementation. Debug. Identify and fix any issues or bugs in code through systematic debugging. Debugging and testing. Test cases validate the program's behavior against a comprehensive set of test cases, including edge cases. Logging and tracing. Use logging and tracing mechanisms to gain insights into the program's execution and identify any issues. Automated testing. Implement unit tests and integration tests in tests to ensure the program's correctness and reliability. Documentation. Problem statement algorithm clearly describe the problem inputs or outputs and any constraints or requirements. Algorithm explanation provide a detailed explanation of the chosen algorithm, including its time and space complexity. Code annotations add comments and annotations to the code to improve reliability and maintainability. Test cases document the test cases used to validate the program's correctness and performance.